Hello everyone, I am Krishnamoorthy Sivalingam from IIT Madras, CSE department. I work in the area of computer networks. In particular, we work on design, analysis, and implementation of protocols and algorithms for networks. Currently, we have three ongoing projects and an earlier project. So we are looking at application of AI/ML techniques for 5G, 6G, and the future networks. We are also working on data plane switches that can be programmed using a high-level language. We are also looking into enhancing the performance of Wi-Fi networks, the current standards and futuristic standards, as well as 5G network implementations using an existing open source software. In the past, we have contributed to the development of the 5G India testbed, in particular the core implementation, and a lot of research is essentially based on that testbed also. In terms of my experience, I have been at India at IIT Madras from 2007. And before I joined IIT Madras, I was a faculty member in the US for about 13 years, from 1994 to 2007. I've guided around 40 MS theses and 12 PhD theses. We have had funding from various agencies, including Sienna VMware, which is ongoing right now. In the past, we have had support from DOT, DST, IBM, and Tata Power Company. Currently, we have one PhD scholar in our group, Kevin Kumar, and four MS scholars, Adarsha, Sai Divya, Kanchan, and Nikhil. So I'll give an example of a couple of research problems where we apply AI/ML to networking issues. So in this work, we look at what is called slice admission control. So in 5G networks, we can have an underlying infrastructure which has a lot of routers and switches, and as well as a data center kind of environment where I can run these so-called slices. A slice is nothing but a virtual share of the underlying infrastructure. In such a network, I can have multiple slices which are virtualized on top of the infrastructure. So when a slice comes in, it gives me various requirements in terms of bandwidth requirements, CPU, memory, and so on. And the admission control problem is to decide whether to admit a new slice or not. So this admission module, which you see on top, has been implemented using a deep reinforcement learning (DRL) approach. We are also using a prediction module based on LSTM to predict what will be the future resources for these various slices and then adapt the resource allocation based on that. The details of this have been published in a paper that you can find online. We also looked at applying machine learning techniques to Samsung phones. There's a PhD scholar working at Samsung who's been looking at this. So in this work, what we try to do is there are several applications that can be running on a mobile at a given point in time. And some of them could be web downloads, some of them could be actual video calls or games and so on. And unless you treat them differently, they will end up affecting each other in terms of throughput and delay and so on. So what we have done is try to build a learning model that prioritizes, that first predicts or classifies what kind of traffic is carried by each connection, and then decide whether there's a video, right, like a teleconference, or the voice call, like a Google Duo or a WhatsApp call, or if it's simply downloading a large file or surfing the internet, and so on. And based on this prioritization, we can allocate resources inside the user equipment, inside your mobile phone, such that you can differentiate them and give them better priority. This is just a sample of some of the problems. Now my students will present their respective works briefly so that you can get an idea of what is going on in our research group. Thank you. Look forward to seeing you sometime in IIT Madras as a research scholar. Bye.
Hi, my name is Suraj Subramanian. I'm working under the guidance of Professor Krishnamoorthy Sivalingam at the DAWNLab. Let me take you through the cutting edge testbed we've built for evaluating advances in the 5G core. The 5G core is the heart of a 5G network. It aggregates data traffic, communicates with the UE, delivers essential network services, and provides extra layers of security, among other functions. Authentication, authorization, and session management are just a few of the services that run on a 5G core. On our testbed that is set up using a cluster of high performance servers running bare metal Kubernetes, telcos, researchers, and telecom equipment manufacturers can deploy their containerized network functions and empirically evaluate the real-time performance of the individual network functions and the core network alike. The observability and the instrumentation that we have built in the testbed help these players gather early insights on how a certain implementation of a core network function would perform at commercial scale. Currently, we have compared open source implementations of the 5G core, such as the Open 5GS, Free 5GC, and the OpenAir interface, and benchmarked their performance at a scale of 60,000 UEs. We are also evaluating the efficacy of various scaling strategies such as the vertical pod autoscaling, horizontal pod autoscaling, both of which work out of the box based on the resource utilization, against event driven autoscaling that scales network functions up and down based on domain metrics. The results from this evaluation helps operators size their infrastructure appropriately as well as choose the appropriate scaling strategy that caters to their specific requirements. Thank you.
Hi all, my name is Krishnamoorthy. I'm a MS scholar at IIT Madras. Currently, I'm working on scaling of virtual network function or VNF in 5G and beyond network. So what is scaling? Scaling refers to adjusting the resources allocated to VNF based on demand. What is VNF? In 5G, network services like firewall, load balancer, gateway are no longer tied to physical hardware. Instead, they exist as VNF in a software defined environment. Today, internet traffic is very dynamic in nature. Due to increase in number of connected devices, scaling of VNF is needed to ensure high network performance, and virtualization of network functions helps in providing scalability. Next question is how to scale. There are two main ways: reactive scaling and proactive scaling. Reactive scaling, as name itself suggests, it reacts when network performance has already degraded. Whereas in case of proactive scaling, traffic demands are predicted and preventive measures are taken in advance. Prediction of traffic can be done using time series forecasting models such as LSTM, GRU, and transformers. Now, you might be wondering, where does all this comes into play? When you take out phone from your pocket and you start browsing internet, there are many steps involved in background to set up the connection for the user. One of such a step is establishing a PDU session for the user. You can see a simplified diagram on the screen of how actually a PDU session is established for a user in 5G networks. Next, let's see one of the ways of how scaling actually take place while establishing a PDU session. We have network of VNF talking to each other. The whole system is being monitored, and whenever a metric is triggered, the scaling action is decided, which are then employed by the load balancer. So that's all from my side. I hope I was able to shed some light on ongoing research. Thank you so much.
Hi, I'm Saitavya, MS scholar working under Professor Krishnamoorthy Sivalingam sir in DAWNLab. I'm currently working on ML algorithms on programmable data plane switches for anomaly detection. Programmable switches equipped with P4 provide flexible header processing, allowing fine-grained control over packet handling. They are essential for detecting anomalies like DDoS, high latency, or unusual bandwidth usage. In such cases, real-time detection is crucial for swift responses. To achieve this, machine learning models such as random forest SVM or any other neural networks are trained on packet features like flow count, packet size, latencies, etc. Once trained, these models are deployed either in data plane or in control plane to monitor traffic. The flow of operation begins with the programmable data plane switches collecting flow statistics like packet headers, traffic rates, etc. These raw statistics are processed to extract features such as mean, variance, flow duration, which are fed into ML model for real-time anomaly detection. When an anomaly is identified, the switch trigger an alert to the control plane for traffic handling or mitigation. This method provides low latency detection and action which scales across multiple distributed switches and ensure real-time response to potential network issues. Thank you.
Hello, I'm Vasudha. I'm a research associate at DAWNLab. My work focuses on fingerprinting on programmable data planes for enhancing network security. Fingerprinting plays a key role in network security by analyzing packet flows to detect and classify different types of traffic. Traditional fingerprinting methods, which often rely on the centralized servers for signature storage and analysis, pose significant challenges by creating bottlenecks and delays, making it harder to keep the network secure in real time. Offloading fingerprinting to switches eliminates the need to rely on a central entity for signature updates, allowing network operators to maintain a constantly up to date database of signatures directly at the network's edge. My solution specifically makes use of programmable parsers, which are an essential feature of programmable data planes and provide greater flexibility than traditional parsers. These parsers can be customized to process traffic with new and unknown patterns in real time, adapting to the constantly changing nature of network traffic and threats. By combining the high speed processing capabilities of Tofino switches with fingerprinting, network operators can gain a flexible and scalable solution that allows them to respond dynamically to new threats, all while maintaining optimal network performance and control.
Hi, I'm Adarsha, MS Scholar working in DAWNLab. I'm working on the problem of heavy hitter flow classification. So network flow consists of the heavy hitters or the elephant flows. For example, you are downloading a file from a server. We are downloading a movie of 3 to 10 GB. That will be classified as heavy hitters, whereas the WhatsApp data, which consists of few strings, will be classified as the mice flows. The heavy hitters needs more network resources, which will hinder the development of the mice flows, which will make mice flows wait longer. So we need to treat them differently. Also, there are many other applications because of which this heavy hitter problem is being studied from a while now. So we are working on heavy hitter flow detection algorithm where with the least involvement from the control plane, we will classify the flow as heavy hitter or not. Also, it's not the case that we will wait for the file download to complete and then we'll say based on the packet count whether it is heavy hitter or not. We need to predict it early so that we can treat them differently. So elaborating more on this, let's say packet comes into the data plane and data plane based on some features like packet inter-arrival time, that is the time gap between the two packets, it will classify the flow as heavy hitter or not. And some network application will take this feedback, it will see whether the flow is heavy hitter or not, and then it will treat the heavy hitters differently and it will give the feedback to the control plane saying the extent to which this classification helped it. And control plane based on this feedback will decide the thresholds for those features, and these thresholds are being used by data plane to further classify the flows later in time, and this cycle continues. So this is what we are working on. Hope this helped to create some interest. Thank you.